discussed last class? I hope I'm audible.
Yes, sir.
So okay. Yesterday we discussed biasing. So I repeat what is biasing in a better way. So we are going to design amplifier. We're going to design an amplifier. So ultimately, using a transistor, one of the main application is amplifier. So till now we have discussed some circuits, that is application of transistor as a switch. Okay, was either on or off. So in that case, transistor was operating in a switching region, that is off or on, that is cut off or saturation. Right now we are going to for the linear operation, right? That means amplification. Our input is having some value like this, some waveform. So I need my input to be amplified perfectly. Frequencies should remain the same, right? Frequency should remain the same, and the amplitude has to be amplified. Okay. So here there was some question. If I am amplifying a signal, say for example, I have small signal like this, small signal like this. So amplifier output is the amplified version of the input. So what is this energy conservation principle is disobeyed here? Is it like that? Is the energy conservation disobeyed? The input is small amplitude, output is higher amplitude. How is this possible? Energy cannot be created nor destroyed. So how is a device, any system or a device, is going to give a bigger output than its input? Energy cannot be created, right? So how it is creating some energy, some work, extra work from nothing?
So we are giving some external energy in the
Yes, that is
amplification.
called yes. Very good. So that is what we are trying to discuss. It. We are giving bias. Bias is not a signal. So this is something we need to. This is bias. This is biasing, right? So this is the bias signal. This is the DC bias. So here I'm just considering AC. Input is AC. I mean, in the sense like it's a fluctuating signal. Output is also fluctuating signal. But here I want to give some DC also, DC ground and DC only I'm giving. That I'm not excluding because that I'm anyway that is power supply, so it's not a signal. So we have to remember this DC biasing is what we are fixing the DC operating point of a transistor. This is very important. So yesterday we were discussing how we are fixing the DC operating point of the transistor, right? Else the amplification will not be proper. For example, I'll give you some example. Suppose I want to amplify a small signal coming from your smartphone. Smartphone have a small gyroscope. What is gyroscope? As you turn the smartphone or any system or device, it measures the angular rotation, the acceleration or angular rotation with which the so that is called gyroscope sensor. So it will give me some signal like this. I need to amplify it. So while I'm amplifying it, I'm expecting my output, which is exactly amplified version of my input. That means it will be something like this. I'm expecting something like this. But sometimes what happens is some clipping happen. What is clipping? My signal may get distorted like this. The top portion of signal may not get in the output. This is called clipping. Okay. So this is something which I don't want. Sometimes maybe bottom portion. Bottom portion may be clipped. So this is all the problems happening. Sometimes we can see the frequency shift also can happen. Sometimes if it is not properly amplified, your frequency also can be become something different, and some distortion can happen in some region here and like that. Okay. So there are a lot of problems which can happen. So in order to avoid those problems, what we have to do is we need to fix the operating point of a transistor. Okay, so operating point of transistor is the DC operating point, or with the input is, or the output is riding. For example, so here, what is the significance of operating point in an amplifier? For example, operating point is that point or which your output is riding. For example, I can give you like this. This is input is this, on output is like this. This is the output. For example, I'm just giving an example. Here, there is a point over which your output AC signal or a fluctuating signal is riding. For example, this can be 3 volt, 3 volt, right? This can be 3 volt. The middle, this 3 volt, and maximum. And after above 3 volt, there can be maybe 2 volt extra, making it 5 volt maximum here. And below also this can be some, below also it can be some voltages, maybe 0 till 0 volt, 3 volt. So you can see this 3 volt is over with my DC signal or over with my AC signal is riding. So this is fixed by the DC Q point. Yesterday we discussed Q point, right? This point cannot go higher because it will get clipped. If it goes higher, what happens? If the shift to higher point, what happens? The top portion get clipped. Now I don't get the top portion. Bottom portion I may get it. I cannot move it down also. Again, the output will not be proper. The output will be clipped. Okay. So this is the importance of this point, DC operating point and Q point. Okay. So amplifier is amplifying the input signal and the energy. It has to be given proper DC biasing. It's called biasing, where you fix the uh, transistor operating point. Especially when you think of operating point, we are concerned about output operating point. Output operating point, we discussed the collector emitter voltage and I collector current. These are the output parameters or points which we are concerned. Okay. So when we think of output characteristics of an amplifier, VCE and IC are the most prominent one, right? Because they fix the exact midpoint of your signal or which the signal is riding. Okay. Now we'll see how we are going to fix this transistor operating point. So, let's. Yesterday we have discussed the circuit. That is, we have simple. This is most simple type of circuit. It's called base bias. Okay, because we have simple base resistance RB. And so we have VC. This is RC. This is VCC. This is VBB, and we have this grounded. Okay. Now here we know this operating point beta is the okay. I hope I'm audible here. I have sufficient range here.
Yes, sir.
Okay. So I think someone is still trying to join, but I'm not going to allow from right now because it's going to disturb the class. Okay. So we have beta. Yesterday we have discussed about beta. Now, uh, now what we started yesterday? First find IB. What is IB? What is IB? Okay, IB equal to, IB is nothing but we just calculate in the base circuit, that is VBB is the driving voltage minus VBE diode drop divided by RB. Okay, so we calculate IB and then we calculate IC. Now this is the IC. IC is beta times IB. Beta times IB. Okay, so we got the operating current of a transistor. Now what is the voltage, output voltage we are concerned about? That is VCE. This is the collector, this is the emitter. So our output voltage is VCE, collector emitter voltage. Okay, that we had discussed yesterday. So how to calculate VCE? VCE is nothing but Kirchhoff law. We should have VCC, that is the voltage drop, sorry, voltage driving the collector current minus drop across RC, that is IC RC, right? So we'll get the VCE, voltage across the, so we got the VCE and IC. So this is the operating points of the transistor. Getting? Now you can see ideally what we want the operating point of a transistor to be fixed, right? So let's see what happens if the operating point is not fixed. So we have drawn the Q point. This is called load line. So what is load line? Now we'll discuss what is load line. So mm, so when you're designing a circuit, the designer is interested in exact Q point or operating point so that he can know where is my output going to swing, which point, that is IC by VCE, right? But there's the chances that your uh, Q point or the operating point can shift. So the designer should know what are the possibilities. What are the possibilities of my operating point, even if it is shifting. Even if it is shifting, what are the possibilities where my operating point will be lying? So that is called load line. Okay. So for example, let me write the equations what we had derived. So VCE, collector emitter voltage, equal to VCC minus IC into RC, right? Now, what is the maximum possible voltage of VCE from this equation? Maximum voltage of VCE is nothing but VCC when IC becomes zero, right?
Yes.
Right. IC is zero. IC can become zero also. If we if okay, at least for analysis purpose we can calculate like this. IC can be zero. So if IC is zero, we know VCE. So we should know that the axis of this graph is VCE, output kya VCE versus IC. Okay. So when IC equal to zero, what will be the value of VCE? Equal to VCC. That means an IC is zero. This is the point. IC equal to zero. This is the point when IC is equal to zero. IC equal to zero at this point. So what is the value of VC is equal to VCC. So I'll mark this point here. So this is my first point in the graph when IC is sorry IC is zero, VC equal to VCC. This is the point VCC, right? Because the IC equal to zero in the y-axis. Okay, so we got this point. This is IC. This is VCC, comma zero, because IC is zero. So this is the maximum possible voltage across VCE. Okay. Now, what is the minimum voltage of VCE possible? VCE can be zero when VCC equal to ICRC, right? So when VCE equal to zero can happen, VCC can be zero. VCE can be zero even VCC equal to or VCC minus ICRC is zero. That is VCC equal to ICRC, right? If this possibility exists, my VCE can be zero. So that means VCE can be zero means this region. So at that time, what is IC? IC is going to be maximum. IC is that nothing but VCC divided by RC. Okay, this is maximum possibility. You can see from the equation. Maximum possible of IC comes when VC equal to zero, because IC equation, IC equation is VCC minus VCE divided by RC, right? In this equation, you should remember we are not changing the VCC because that is we are keeping it fixed. We're keeping it fixed. In a circuit, VCC is fixed based on the technology or the power supply available or the designer constraint, whatever. So we are not going to change the VCC and RC right now. We may change later, but at least for time being, VCC and RC is fixed. We already designed the power supply and resistance, everything. Now we can see when VC is something which variable. So when VC can be zero, when my ICRC equal to VCC, right? So we can say IC maximum value of IC can come when my VC equal to zero. That means VCC divided by RC. Okay. Now I'm going to plot this point in the graph. IC is maximum, VCC by RC. So this is the point at the top when VC equal to zero. So this graph point is 0, comma VC, sorry, 0, comma IC. IC. Oh, IC is coming from VCC divided by RC. Okay, so these are the two extreme points which I may get in my output characteristics. Okay, so one is zero current, maximum voltage, that is VCC across VCE, across output of transistor, and another is maximum current when VC equal to zero. VCC, that is VCC by RC, is the maximum current possible. Okay, now if I connect these two points, extreme points, what I'll get? If I connect these two extreme points, what I'll get, this line, there I'll get a line. This is called load line. Okay, so I connected these. So this load line. Now this line is called load line. Load line, very important concept in the amplifier and the biasing of a transistor. And load line. So what is a load line? Load line is a line connecting all those points, all those possible operating points in a transistor or a amplifier. Against an amplifier for more better light. So whatever we discussed yesterday, the Q point, the quiescent point, or the operating point lies in the load line only, right? So you can see load line. What are the factors it depends? Load line depends on the fixed factor, that is VCC, that is power supply. You can say VCC and RC. So we can say load line is something which dependent upon the fixed parameters. As a designer, as a RC is already fixed, VCC is fixed. So based on that circuit parameters, I am drawing the load line, right? VCC is already fixed, RC is already fixed. Now, till now, the transistor is not at come. You should remember, we are not at plotted the characteristic of transistor yet, right? Now we are plotted the characteristic of load. Load means we can say the power supply and RC, the resistance. Now, now over the load line, now I plot the transistor characteristics. Right? Now plotted the load line, maximum possible IC, maximum possible VCE across the transistor. The transistor has not come yet. Now over this load line, I'm going to plot the characteristics of our transistor. So what happened? Over the load line, I'm going to plot the transistor characteristics. For example, green. Yeah. So what happens? Now I plot the transistor characteristics, something like this. This is the output. This is the character VC versus IC of the transistor. Now what happens? Now I can get a point which is intersecting. Both are intersecting at a point. So this point is your operating point of the transistor. Okay, so load line, it definitely passes through the load line, and based on the transistor temperature and different factors I see, my operating point is going to vary. So this is my operating point. Operating point, nothing but Q point. Okay, which tells me what is the IC and VCC of the operation, or the operating characteristics or operating point of the transistor. This is Q point. Now by some point, if I change the base current or something, I get a new Q point. How? Because now I'm going to change the base current. I'm reducing the base resistance. Right now you can see load line doesn't depend upon base resistance or base voltage or base current, nothing. Now again I'm changing the base current or base voltage or something. Now input parameters are changing. Now the Q point is going to change. Now the new point is like this. Right? The Q point is changing. Now the new Q point is here, the setting point of the load line transfer characteristics. Now you can see the variation. The VC has increased, but IC has increased. Okay, so you can see this operating point has changed. Suppose I increase the base current. Load operating characteristics now new point is Q point is here. Operating point is okay. Now one more operating point I'll draw in the bottom here. Where the operating point will be Q point will be here. Among this, which is the most preferable point as an amplifier, as a designer, where I want my operating point to lie? These are the Q points, different Q points. As a definitely you can tell me that I don't want my Q point to lie on this point. Where first of all this is a bad. Now this point is also bad. Who can tell me why? This
So
why
because
this?
there is no much length to vary our signal.
Yes, there is very less there to vary our signal. Definitely, you're right. Yeah, why? Because if I vary the signal at this point, what happens? At this point, you can see the voltage is limited. If I have negative voltage and positive voltage, I cannot have. Why? It gets clipped. Why? Because this is maximum possible voltage. DC is maximum here. So this point will be clipped. Right? I'm missing this point. So my output will not be properly amplified. It will be clipped. Right? One side positive. And the same time also, this is near cutoff point. So this is near cutoff point. This is near cutoff point. So I cannot So I cannot allow the operating at that point because it is near cutoff point. And another point is here near saturation point. This near saturation point. Here also the same thing happen. Here what will happen? You can see IC fluctuation will be very less. I cannot fluctuate my IC here because IC will be clipped. IC will be clipped on this point. because there's limited maximum IC possibility is ICC VCC by RC, so I cannot go. So again, my IC is clipped here and my waveform is not proper. Okay, if you see the bottom also, you can see the bottom VC also clipped here. You can see VCC can also be clipped here. This point VCC is going to be clipped here also. Okay, so I don't want to operate my transistor or amplifier in these extreme regions. Okay, I don't want my transistor in this extreme region because output is going to be clear. Ideally, what I want? Ideally, I want the operating point to be center, right? This is ideal point. You can say ideal center. Right? So this is ideal point, ideal operating point. Okay. So why? Because I have maximum fluctuation possibility. Right? So I can have maximum, VCC can be fluctuating this freely here, and same time it can also be fluctuating maximum without any clipping. Right? Okay. So this what the lines of the load line depends upon the things VCC, RC, that's it. And if you go to the maximum IC and maximum VC, and that is the load line. So load line is different points where your operating point of a transistor or okay. Based on the load line, then you put the transistor. Now you use this transistor. Now you there's a base current, base voltage. There's a beta. A lot of things come into play. Then you know the transistor character. So the intersection of the transistor characteristics and line, the load characteristics give the operating point. Okay. So load line. Uh, Along with load line, if we plot the transfer characteristics or input characteristics, beta, all those things, we'll get the operating point. So operating point ideally should be in no, no, sir. Even operating point, suppose our transfer is operating at this point, nice point, but there may be some changes. If it ideal case may if you have designed something fixed, we are happy and everything is working fine, but it doesn't happen in the practical sense. And this makes life of an engineer or designer very difficult. We have to be prepared. We have to prepare ourselves and our circuit or our design extreme situations. And there are situations where our Q point can vary automatically with respect to temperature, maybe with respect to even collector current, and there are other pressure, humidity, whatever. There can be different non-ideal situations where our Q point is going to vary. So if your design or amplifier working in Antarctica is not working exactly like in Delhi, and the same thing in working in Delhi is not exactly working in New York or so this is not good. It is very different circuit having different parameters here, and this doesn't is not good. So this is a problem. So as a analog or analog circuit designer, you have to fix the Q point. Your circuit should be independent of all those external parameters. Right. So this is the challenge of the designer. You have to fix the Q point or the operating point of transistor so that you have good proper amplification. Okay. So this is another point is the beta. The beta also can vary. So another important point is beta is also varying. So then this makes life of an engineer very difficult, especially analog designer. Okay, digital designers don't have this problem. They are not concerned about these circuit level things. They are just happy with ones and zeros, and they are very simple. Okay, okay. So, but analog designer, we have to know a lot of variation, a lot of thinking has to be done. So here, if I draw the beta, for example, I'm giving a sample of beta. So beta, this is beta DC gain. Okay, DC gain or DC beta or a lot of HFEs. Called also HFEs. There's some other terms called HFE. In your if you've seen anyone has seen a data sheet, there may be a term HFE. So this is also nothing but beta DC gain. Okay, so based on the IC also sometimes based on the IC also beta can vary. For example, the beta I'm just giving a range. For example, my beta is ranging from 50. This is 100. This is 150. This is 200 and this is 250, something like this. My beta is varying. So let's see the graph. The graph will be sometimes looking like this. This is a real case, something like this. You can see how much variation beta is happening, and IC is increasing. You can see beta is initially small, maybe it was 50 or 60. Now it is increasing to 150 at one, and again maybe it goes to maybe 1 or IC. So this is something I want. I don't want my beta If the data is changing again, like vary my IC again, VT, so it will vary my operating current also. So this is a difficult situation. Now this is I'm keeping a fixed temperature. This is another important point. This say for example temperature is equal to 30 degrees Celsius. 30 degrees Celsius. Now if I increase the temperature, what happens? You can see another graph. This is the most difficult part. Now if the temperature increase, sometimes I'll get this graph. Now this is temperature equal to say for example 40 degree. Now if I reduce the temperature, I'll get another graph. So temperature reduce, I'll get this graph. This is T equal to maybe 10 degrees Celsius. So you can see based on the temperature also it is varying, beta is varying, based on IC also it is varying. So this is a lot of non-ideal things coming into picture. So if you see the data sheets, you can see the beta variation of any transistor with respect to IC and temperature something. This goes on like this. They'll show like this nice based on different temperatures. So it's not easy to design a perfect circuit which works nicely. Okay, so a lot of things come into play. Now the designer, what is the challenge of designer? In order to design a circuit which is independent of all these changes in temperature, changes in IC, even changes in beta as a result, it is the main aim of a circuit designer. Okay, so now let's see what will be our simple circuit what we have designed is based by our circuit, how it will be varying based on the temperature or something. So we can see this is not a good circuit in terms of stability. Okay, why I'm saying is it unstable? Because my operating point is changing. Based on my operating point, my things are varying, which I don't want. My operating point will be varying, all those things. So this is RB, this is RC. Now this is we as we already discussed, we are showing here only the DC points of a transistor. We are not interested in AC points. Not interested, not right. Not we are interested, but we are not discussing that right now. But if you need to know how it works, it is working like this. How we give the AC? AC is given like this. We need to have small ACs, maybe some sensor. I have an AC. This has to be given to this. How we give? One option is yeah, this is a sensor, and I can directly give this to here, right? And output what I'm getting output is getting from this point, so I'll get the output from this point. So this is amplifier output. I'll get it from the output and I'll give it out, but this doesn't work in practical scenario, right? Why I'm giving to base? Because the base, this will vary my base current, slight variation in base current. So the slight variation in base current will be reflected in the collector in amplified way, so I'll get a amplified. This is what I want, but here some problems can happen. One problem can happen is the base voltage, the DC voltage and AC voltage can get mixed together. Sometimes the DC voltage can come to this AC sensor, your gyroscope, and it cause problems there. And the DC voltage can also come into your output and cause a lot of problems also here. Although AC doesn't have much, so because it is just fluctuating, magnitude is fluctuating. So DC batteries and is not affected much by the AC. But DC voltages can affect your sensors, can affect your output load. Maybe your output load is some loudspeaker. The DC goes to loudspeaker, it'll have some lot of noises. I think you have given. You can try giving some buzzer. I think you know about buzzer. If you give a DC voltage, it is vibrate. So DC operating point can come into your input sensors or something, or it can also come to your output. So what we'll do, I need one device or one device or one you know one thing which doesn't allow DC but allow AC. What is this parameter? What is this component? You can say what is that component which allows AC but doesn't allow DC current to flow through it? I need that thing. What is that? The component which allows AC to flow through it but doesn't allow DC to flow through it.
So capacitor.
Yes, capacitor. Yes, capacitor. You can see, what is the impedance of a capacitor? We know capacitor, XC, impedance of a capacitor. How we write? 1 by C omega, right? Right. So what is the meaning of this? The omega, what is omega? 2 pi into frequency. So 2 pi into frequency. Yes. So the capacitance has a effect on the frequency. You can see the frequency is increasing. The frequency is increasing. That is a denominator. axis is going to decrease. That means impedance offered by the capacitor to AC is very negligible, very less. As the frequencies increases, the capacitor impedance is going to, or reactance is going to decrease. Reactance and impedance, as the reactance is a part of impedance, impedance is nothing but the uh, reactance square plus resistance square, root of that is impedance, right? So if the reactance is less, my impedance offered by the capacitor to the AC is less, right? So the frequency increases, the capacitive reactance decreases, and at the same time the frequency decreases is going to DC, capacitor is going to, the value in reactance is going to be very high. That means it's going to be very high. That means impedance to the DC or non-fluctuating current, constant current or voltage is going to be very high capacitor. So what I'll do, I'll use a capacitor here based on this principle. I can use a capacitor. Capacitor doesn't allow the flow of DC, but allows the flow of AC. So I'm keeping capacitor here. This is called coupling capacitor. Okay. Now the DC doesn't flow to my sensor, but AC can flow from the sensor to my amplifier. Now output also I should keep a coupling capacitor. Okay. So this is V out, AC out amplified. Okay. So my AC has EC path. How AC comes? AC comes from the sensor. It is amplified, and this amplified and output to the collector emitter terminals of the transistor. So we can see the transistor output is getting from the VCE, collector and emitter terminals. This is VCE. Okay. To be very clear, the voltage across the collector and emitter terminal is being output from the transistor or the amplifier output. Okay. Other things are biasing. So all the things VCC we have to give for the biasing, fixing the operating point, fixing the Q point, okay, making beta stable or whatever, all other things. Okay. Now this is the overall picture what we are trying to discuss. Now the question is how we are going to fix the operating point. Now from the base circuit we have seen it's not a good circuit because beta is depending on beta that we have discussed. This is okay. This is what I wanted to show. So this is my this is called base bias circuit. Base bias circuit. So we know the current equation and voltage equation of this, but this is not a good circuit because my IC also depends on IB. Sorry, IC directly in the equation it depends on IB, right? Because IB, IC is dependent on beta also. Beta can vary also. If beta varies, IC can vary. So there's always a beta. We have shown the graph of beta also. So I don't want the IC to change with respect to beta. So what is the solution? So if I change something in this circuit, I can have better circuits. For example, I may change this RB from here. I may change RB from here and put in the here. So what change you have done? I may change the color so that you can see the differences. I have changed the RB from the base to the emitter. So what happened? No change happened, but a new resistance came in the emitter. This is called RE emitter. Now what change is giving to circuit? We'll see. Is going to be dramatically change the circuit operation. Now my circuit is more stable to the beta variation. Even if beta is varying, my circuit or operating point is not affected much. Okay, so in last graph, an operating point VC versus IC, you can try, you can see different beta and see that the operating point varies hugely from the saturation to cutoff. We can see, but here if I put RE here, now what is the, let's calculate the new equations of IB. So we know that this is VBB. So this is base, this is emitter. So this is emitter here, emitter E. This is C. Okay. Now let's calculate IB here. What is IB here from this equation? Or at least what is VB from here? We are giving VBB here. We are giving VBB here. VBB. VBB here. Okay. From here, how will we calculate the IC and VC? Ultimately, we are interested in two things. That means we are interested in VCE and IC. These are my operating things. To fix IC and VC, we have a lot of biasing techniques. That is what different biasing: base bias, voltage divider bias, emitter bias. Now this is called emitter bias. This circuit which we are going to discuss is called emitter bias. Emitter bias. Emitter bias. Emitter bias. Okay. Emitter bias circuit. Now what is the specialty of emitter bias? It is independent, or it is not depending much on the beta variations. Now how it happens that we have to show here. Now what happens here is, let's calculate IC and VC. Your only point is you come to derive the equations of IC and VCE and see whether it is independent of beta or dependent of beta. If your equations while deriving IC and VC is depending upon beta, then you know the circuit is beta dependent circuit, and that may cause instability problems and high temperature or variation in current. So what I want to derive in such a way that my equations of IC and VC doesn't depend upon beta. Now here you can see I will derive IC. From this circuit we can see IC is something which flow in the output circuit here. So how to start? If I know the voltage across this VE, that is V emitter, that is this V voltage across this point, I can calculate the IC or IE. So this current is IE. So this current passing through the RE is nothing but IE, right? IE. Okay. So IE is passing through the emitter circuit. So here, what is VE? Let's try to calculate what is VE. VE is nothing but we are giving a VBB in the input minus VB. VB, that is nothing but 0.7 in silicon, we know, right? So we can write an equation. V emitter voltage is nothing but VBB, that is potential applied across the input, minus VBE, right? VBB is the input, VBB, which is minus, which is subtracted. When we subtract VBE from that VBB, we'll get VE, voltage across emitter, right? Right now, what is VB? VB, we know it's a constant for silicon or germanium. Silicon, it is 0.7. So I got VBB minus 0.7. So this is my V. So I got VE. Now we know the voltage across the resistance. So how to get the current of the resistance? You know the
V
voltage
by
across the,
RE.
yeah.
VE upon
What
RE.
is, repeat? Can you
V
repeat?
VE upon RE.
Yes, yes. So this is, yeah, this is, you're right. So VE is nothing but voltage across end resistance, nothing but current flowing through the resistance into resistance itself. V voltage equal to IR, V equal to IR. So V is nothing but IRE. So RE we already know. So IE we can easily calculate. What is IE? I is nothing but VE divided by RE, right? So here we are deriving IE. Now the next point is how to calculate IC from IE. And here for all practical purposes, you note this point. We can consider this very important step. That is IE approximately equal to IC. This is one simplification which we can apply in any BJT transistor circuit. IE approximately equal to IC. We know at beta is tending to very high, or alpha is, you know, what is alpha? Is around 0.99 something, 0.99. That means alpha is nothing but IC divided by IE. If alpha is 0.99, that means IC is approximately equal to IE. Ideal value of alpha is equal to 1, or beta IB is 0. So IC should be equal to IE. But practically alpha is around 0.99, 0.98 something. But all the analysis purposes, as circuit designer, we need to analyze very fast. So slight changes we can neglect. So we can say IE is approximately equal to IE here. So from this equation, I derive IE from the VE, that means voltage across emitter resistance. And from that, if I divide by RE, which is already given, I'll get the IE. And from IE, I can get the IC. Okay. So what I got? I got IC from IE. Okay. Once I got IC, I can use the same equation to get the VCE. What is VCE? VCE is nothing but VCE is nothing but, we already know IC, nothing but VCC minus ICRC. So same equation works here, but you can see in all those flow, we are not use beta at all. We are not use beta at all. So this is circuit is better than the base bias circuit. Okay, because we in our driving we are not use the beta. Okay, so this is called emitter. It's called emitter bias. This is called emitter bias. Okay, so I'll just once again explain. Initially we had a base resistance RB, okay, and RC. So what I did, I changed the base resistance into the emitter side. So then it becomes emitter bias. Now there is no beta in deriving IC and VC, so it is beta independent circuit. Emitter bias is beta independent circuit. Okay. Now, uh, now I'm showing another bias circuit, voltage divider bias. This is another circuit. It has a lot of advantages than the base. This is another circuit. This is a voltage divider bias. Very important. Now this circuit, voltage divider bias. Okay. So this is this is VCC. I can call VCC plus VCC. Okay. This is R1. Now RB changes to R1 and R2. This remains same RC, and here also we have RE also. Okay. Now this is a new biasing. New biasing. What is the advantage of here? Initially we were using two different base voltages. VBB was separate, VCC was separate. Now that is not a practical thing and not easy also. We are designing something. We need two separate DC voltages. It's not practical. So here it's not much change, but we are using same supply voltage VCC for the collector and emitter. This makes things a bit simple. And let's see what are the other advantages of voltage divider bias. So this name of this biasing is voltage divider bias. Voltage divider bias. So as the name states, it's very clear. We have a voltage divider. This is R1 and R2. There's a divider. Voltage VCC is divided by two resistance R1 and R2. Say this is voltage is V1. This is voltage is V2. For this concept, we're using only one voltage source, and this called voltage divider bias. Let's see what are the advantages of voltage divider bias. Okay, so in voltage divider bias, let's calculate. Well, let's try to calculate the VCE. That is my operating point. That is nothing but my VCE, and IC. This is my operating point. Let's try to calculate VC and IC of the voltage divider bias. Okay, fine. So here also we have the base. The base is B here. This is the base point. This is the emitter, and this is the collector. Okay, so let's try to calculate what is the base voltage. So this circuit, we're interested to find the base voltage first. For the base voltage, then only we can find the voltage at this point. This point, this is very important. This point is voltage. We need to find voltage across the base of the transistor. Then only we can find the voltage across the emitter VE at this point. So we have two resistances, and in two resistances, we are dividing a voltage VCC. Okay, so we know one equation. We know we're going to what equation of V1 and V2 in a voltage divider. So imagine right now, imagine there is no connection between this midpoint and the transistor. So what is the V1 and V2 in this case? We already know. We already studied V1 is nothing but
VCC into R1 upon R1 plus R2
yes VCC
to R1
into
R1
R1 divided by R1
upon,
plus R2, right?
yes,
So this
उसके
is
लिए
my
R2 हो जाएगा
V1.
V2 के
Likewise,
लिए.
you also get V2 also. Yeah, VCC into R2 divided by R1 plus R2. Okay. So here what we are interested, we are interested in V2. Okay, so in the Viva, I asked some students if this is the case V1 and V2 is voltages drop across R1 and R2, which voltage is going to the input of the transistor? That means transistor PBE and this point.
So
So
V2,
a lot of students answered V1. V1 is going to the input of transistor. That is a conceptual mistake. Actually, whenever we are thinking of any voltages across any point, we are considering the voltage at that point with respect to the ground. With respect to the ground. So the voltage input to the transistor is V2, not V1. Why? Because V2 is going to the base with respect to the ground. So B from the base and ground, I have V2, not V1. V1 is floating. V1 is just dropping across this R1. It has nothing to do with the transistor input. It is actually V1 is drop across base and collector junction and the RC. Should know that. Okay. I hope I'm not confusing you. This voltage drop across
no sir,
R1. Yeah, voltage drop across R1 is base, collector, and RC. But the input to the transistor is base emitter. So V2 is going to the base emitter. So from that we are interested in the V2 here. Okay. So first find the V2. Now we can know V2 is nothing but the VB. So this V2 we have found is the VB base. Okay. So what we are trying to do, we are trying to simplify the voltage divider circuit. Okay. So maybe it is just something confusing. So I'll just try again. Very simple. Two resistances, then the transistor, again RC and RD. So this is voltage divider bias. Okay, and my one voltage source is VBC. So this is my names of the resistance. This is R, this is R2, this is as usual RC, this is RE. Okay, this is the resistance here. And ground is here. Okay, so this is my voltage divider. Now, what on the voltage V? So this is net voltage VB we have found. VB we have found. Now we can use the same equations which are used for the emitter biasing circuit. That means now VB is drop across base emitter and base emitter voltage and VE and resistance. Resistance also has some voltage, and that is VB. VB is equal to VBE, base emitter drop, plus V emitter of the transistor. You can see we are using the Kirchhoff law only. VB is input, this drop across the circular path. We are using the Kirchhoff law. VB is drop across VB and VE. Okay, so right now we also know, VB. So VE is nothing but VB minus 0.7, because we know transistor voltage drop for a silicon and germanium is constant. So we got VE, right? Now, once we got VE, we can easily calculate IE. IE is nothing but VE divided by RE. So what's the advantage? From the value of RE, we got IE. Again, we use the same approximation, which is very important approximation. IC approximately equal to IE. For all practical purposes, we can take this. Now we got IC. Now we should know that we are not using beta yet. So this is also beta independent circuit. Now we got IC. Now again, we have to calculate VCE. Now VCE, how to calculate VCE? VCE from here also equal to VCE is nothing but VCC minus ICRC minus IERE also is coming across here. So there are two resistances. Okay. So VC is from here. There are RC is also there, RE also there. So the equation is the Kirchhoff law in this circuit. Now I'm using Kirchhoff law in this circuit, closed loop. VCE equal to VCE drop equal to total supply voltage, that is VCC, minus drop across this resistance RC, that is here, and drop across this resistance RE, that is here. Okay, so VC is VCC minus ICRC IERE. So this is the equations of operating point of, we got VCE and we got IC. And here also you can see there was no beta, but this is also beta independent circuit. Okay, so I think it is clear. The concept is clear. What is the advantage of voltage divider bias? And okay. Now, before I think I want to discuss one more important point. I think this is sufficient. We'll take some examples. We'll take examples are very important. This is your questions. You can expect definitely questions in the exam from this. I will give you a circuit and you have to calculate the IC and VCE. That is nothing but the operating point. So this is IC, this is VCE. VCE. Okay, so we'll have different operating conditions. Okay, so here we have different, all these points are the different values of IB. This is IB is 40 micro ampere. This is IB equal to maybe 10 micro ampere, and this is 20, 30, 35, something like this. Okay, so different. Now the Q point, operating point of transistor is nothing but this point. I'm drawing the load line. Okay, so load line I'm drawing. Which are the points of load line? This is the zero voltage maximum current, that VCC divided by RC. This is the first point. The bottom current is zero, voltage is VCC. So VCC is zero. This is 2 points. Now our operating point will be lying. Ideally, I want my operating point to the middle. For example, middle of the load line. Here it is. This point may be good, or this point may be a good point. Or I can also see another, if possible. If there is a point something like this is also a good point. Okay, now what is the change in load line if we increase the VCC of a transistor? What is change in the load line if we increase the VCC of a transistor? For example, that let's discuss that concept right now. Suppose I have a transistor here and I have some VCC keys here and this. Okay, here if I have initial load line like this, initial load line is like this. So what'll be the new load line if I change the VCC? If I change the new VCC from 5 volt to 10 volt, I change to 10 volt, what will happen? This is the 5 volt load line. You can see the VCC is shifted like this. It is shifted like this because more current is going to flow, maximum current and maximum voltage is going to increase. Okay, so as I go on increasing my VCC, my load line is going to shift like this, right? Because the maximum current is going to increase. Maximum current is going to increase here. IC maximum is going to increase and VCC drop or VCE maximum is going to increase. As I decrease the VCC, again, you can also reduce. This is parallelly changing. Okay. Now the next question is what will be the change? What will be the change if I'm going to change the resistance only, not the VCC, only resistance I'm going to change. What will change in load line? Okay. So this is my output Kera IC versus VCE. Now I'm not changing the VCC, I'm changing the RC. I'm going to output resistance RC. So what is the change going to be? Resistance is always the slope, right? Slope. So if I'm increasing the RC, you can see the current will be shifting. For initially, for example, my load line was like this. Okay. Now I'm going to reduce the RC. What happens? Reduce the RC means my current is going to increase, right? So current is going to increase like this, but the maximum voltage is going to be same, right? Again, if I increase, what happened? Again, it will be increasing. The maximum current is going to change, but maximum voltage is fixed. I'm not changing the voltage. If I decrease it, what happens? A new RC, but decrease. So right now, I just decrease the RC. Okay, this is RC decreasing. This is RC decreasing. Okay, the different values RC decreasing. That's my current is increasing. So if I increase the RC, what happens? Current is reduced. Maximum current is reduced. Like this, it goes like this. Again, if I increase the RC, again load line is going to shift like this. The different points of load line if I varying the RC. Okay, so this is RC increasing. This is RC increasing. So initial RC was like this, something like this. So the load line is shifting like this. I don't know, someone is trying to. Sunil Kumar and Rajneet. The time is already 1 hour. You're already late by 1 hour. Don't join for attendance. Okay. Fine. So this is the variation in load line with respect to change in RC. Okay. So now you can practice some of the questions in the Malvinum. Malvinum. Okay. So tomorrow we'll take a concept of feedback. What is a feedback? Okay. So feedback is even if there is some variation, even if some variation in the current. So you have to just, and theoretically I'm saying, even if there is a variation in current, is there any self inbuilt mechanism where my circuit or my device can automatically adjust to the current? For example, my load line is like this, okay, and transfer is like this. So my Q point definitely is this Q point intersecting of this load line and characteristics. By some or other problems, if my load line is going to change to here, or operating point is going to change here or here, so it is not good. So if there is a mechanism by which I can automatically shift my load line, that my transfer amplifier operation is not affected much. Okay, feedback mechanism based on output variation, where my VC or IC vary, I'm automatically able to adjust the RC. Right, what is happening? And if the load line is going to shift, what is the meaning of this? That means load line is going to coming here. In case the load line is going to come here. So now load characteristics. What's happening? The IB is changing. No? That is the main thing. IB is here is less. IB here is 10 micro. But IB we expect IB is equal to micro. But it is and here the top IB is 20 micro. So basically what happens is the IB is also changing. We are going to different IB values by changing the beta, changing the temperature. We are having different IC. This is basically IC. You can see this is IC. And this IC change is happening because I maybe the IB change will happen. Beta is changing or temperature is changing or some other ICO, the leakage or the reverse current is changing. So this is having separate IC. This is IC1 maximum, IC2, IC3. So each of this has corresponding IC also. Sometimes the variation in IC can be amplified by the variation also. So for example, here load operating point is changing to the top. So if this is happening, that means my IC is changing. Operating point is changing to new value. So suppose if that happens, if I am automatically able to reduce my IB, automatic, I can automatically circuit come back to the okay. So somehow by temperature or some other means, my IC is increased. So the operating point has been changed. My output of my amplifier is not perfect. So what I'll do, instead of reducing IC, I'll try to reduce the IB. Okay. So if I reduce the IB, automatically IC is reduced. So the point will come back to the initial IC. Same thing happen in the opposite direction. If somehow my IC is reduced, my operating point is reduced. So what happens? Operating point is reduced. What happens? Now, if I'm somehow able to increase my IB, ultimately I'm increasing IC also. So that constant feedback. If something is which is desirable, we are automatically able to change IB so that we are coming back to our native operating point. Okay, that is called feedback. So we will discuss how we are able to automatically adjust IB if our operating point is changing. Very simple. So this is introduction feedback. So I think that's all from today. If you have any doubt, we can discuss right now, or we can put it.